Next we will see de-Arsonval galvanometer. First we will see what is galvanometer. It is an instrument used for detecting the presence of small current or voltage in a circuit. It is the instrument used for detecting the presence of small current or voltage in a circuit or for measuring their magnitude. So, it is mainly used for DC measurement. It is called as DC galvanometer. So, next we will see the application where this de-Arsonval galvanometer is frequently used. It is used in resistance measurement in bridges and in DC potentiometric work. Mostly resistance measurement and DC potentiometric work, this de-Arsonval galvanometer is used. So, in addition to being sensitive, it must have a stable zero and short periodical time for this type of measurement. So, now we have seen what is de-Arsonval galvanometer. So, de-Arsonval galvanometer is nothing but instrument used for measuring the presence of small voltage or current in a circuit or for measuring their magnitude. It is a DC galvanometer. The main application of this de-Arsonval galvanometer is it is used in resistance measurement in bridges and in DC potentiometric work. Next, we will see the construction of de-Arsonval galvanometer. Now, we will see the construction of de-Arsonval galvanometer. Okay, we will see the diagram. This one is the diagram for de-Arsonval galvanometer. We will see what are all the components in this de-Arsonval galvanometer. So, the first component is the permanent magnet which has north and south poles. So, the first one is the permanent magnet. Second one is, so the use of this permanent magnet is to produce uniform magnetic field. Next one is the moving coil. The outermost layer is called moving coil. So, the moving coil. So, this moving coil will be either circular or rectangular in shape. So, the shape of this moving coil will be circular or either rectangular. This moving coil is wounded on a aluminium former. So, this moving coil here it is wound on a aluminium former. The shape of this moving coil here it is rectangular. It may be circular or rectangular. It is wounded on a aluminium former. Next, this moving coil is suspended with the help of a upper suspension and lower suspension. So, for this suspension here they have used phosphor bronze filament used to suspend the moving coil. So, the moving coil is suspended with the help of a phosphor bronze filament, so that the moving coil will be freely suspended in between the air gap of the permanent magnet. Okay. Next one is iron core. So there will be a stationary iron core. So the iron core will be spherical if the coil is circular. So it will be cylindrical if the coil is rectangular. So in this diagram the coil is rectangular, so the iron core will be cylindrical, right. Next one is the mirror. Here the mirror is used for indication. Here mirror is used for indication. So these are all the components of a D'Arsnoval galvanometer. Here we are having a permanent magnet for producing magnetic field. There will be a moving coil which will be wound on a rectangular aluminum frame, and it will be freely suspended with the help of phosphor bronze filament, and the iron core will be placed in between the moving coil, and a mirror is used for indication. These are the components of D'Arsnoval galvanometer. Next we will see the principle of operation. So when a current carrying conductor is placed in a magnetic field, it experiences a force. So here when a current is passed through the moving coil, it will be a current carrying conductor. It will be placed in the magnetic field of this permanent magnets. So when a current carrying moving coil is placed in the magnetic field, it will experiences a force, right. So how the galvanometer works is, when the current flows through this coil which is kept in the magnetic field of a permanent magnet, a force will be produced which will make the coil to move. So the coil will be moving. The force which is responsible for making the coil to move is called as deflection force. So in working, the deflection force is produced which moves the coil. So as the coil moves, the mirror attached with this upper suspension will also be moves, and the reading will be indicated with the help of this mirror on the scale. Oh, this one is the galvanometer I have shown. So I have taken this galvanometer. Here this one is the upper cover. Now I am removing these parts. So this one is the graduated uniform scale which is used for indicating this reading. That is a mirror arrangement in order to remove the errors while measuring. If you see, oh, this one is the galvanometer. So the galvanometer will be having a needle. So the needle will indicate the presence of small voltage or current in a circuit, and inside that you can see a moving coil. Here the coil will be moving, right. So coil will be moving inside the permanent magnet. These are the permanent magnets. So this coil will be wound on aluminum frame kept in between this permanent magnet. In the center we are having a iron core. This iron core will be placed inside this moving coil. So this moving coil, the iron core will be suspended with the help of a spindle. So on the above and below the moving coil we are having a phosphor bronze springs. Okay, this one is the galvanometer. Now we see the working of a galvanometer. As I already said, see what are the working of moving coil. So moving coil is the current carrying element. It will be suspended by phosphor bonds filament so that it can freely rotate about its vertical axis, and it is arranged in a uniform radial and horizontal magnetic field. Next one is the cylindrical iron core is used to provide a flux path of low reluctance. So this will give a strong magnetic for the coil to move in, which increases the deflecting torque, which is represented as Td, and the sensitivity of the galvanometer. So here the moving coil, it is the current carrying element. It will be wound on a aluminium. It is wound on aluminium former, and it is suspended by a phosphor bronze filament. It is kept in a uniform radial and horizontal magnetic field. Here the cylindrical iron core is used to provide a flux path of low reluctance, so which provides a strong magnetic field for the coil to move in, also increases the deflecting torque and the sensitivity of the galvanometer. Next we will see the suspension. So here the suspension, there are two suspensions, upper and the lower suspensions, which also carries current to the coil. So this type of galvanometer, so we are having a upper suspension and lower suspension. So this type of galvanometers must be leveled carefully so that we can get a perfect reading, because if it is not leveled carefully, it will touch the permanent magnet on the either side of the coil, right? So for laboratory purpose, we have to use a galvanometers with so this can be used only for only used in labs where accurate readings are required. So for portable galvanometers, this type of suspension cannot be used. So for that purpose we can use taut suspension. So here in taut suspension, the moving coil will be suspended by the filament having upper and lower springs. So the moving element will be having upper and the lower springs. It will be kept under a tension so that the proper leveling of the instrument is not necessary in case of taut suspension, which is used in portable galvanometers. So in case of upper and lower suspension used galvanometers. The proper leveling has to be done properly so that the accurate readings can be taken. Also in portable galvanometers, the torque suspension is used for the suspending the moving coil, and also it will produce a torque called as controlling torque. This controlling torque will be responsible for controlling the deflection of the pointer. Why this controlling torque is necessary is, once the pointer starts deflecting, without controlling torque, the pointer will swing beyond its steady state position. So the pointer will swing beyond its steady state position. In order to control the deflection of the pointer, this controlling torque is necessary. So the deflection torque is produced by this moving coil and the controlling torque is produced by this suspension. So the working is, when current carrying conductor is placed in a magnetic field, it experiences a force. So when a current carrying conductor is placed in a magnetic field, it experiences a force. So here the current carrying conductor is the moving coil which will be placed in the magnetic field of a permanent magnet. So the force is exerted on this galvanometer. So the deflection force is produced which will make the moving coil to rotate. So since the moving coil is suspended with the help of a suspension, that is, which has a spiral torque suspension, we have two springs on the top and the bottom of the suspension, that springs will produce a controlling force. So this deflection force and controlling force will oppose each other and will make the pointer to rest at a particular position, which will indicate the amount of current flowing through this coil. The deflection force which produces the deflection torque will be directly proportional to the amount of current flowing through this circuit. Similarly, the controlling torque Tc, which is produced by the springs, which will be directly proportional to the deflection of the pointer, right? So the deflection torque will be directly proportional to the amount of current and controlling torque will be directly proportional to the deflection of the pointer. So what happens is, the pointer will rest at a particular position. Okay. Now the deflection force produces a movement of the coil, controlling torque will control the movement of the pointer. But in order to make the pointer to rest at a position or to indicate a value to be measured, we have to produce a force called damping force. Damping force is nothing but to reduce the oscillations in the pointer and to make it to rest at the final position quickly, we need this damping force. We know that the pointer will oscillate before reaching its steady state position. In order to reduce that oscillations, this damping force is produced. We will see how this damping force is produced. We will see how this damping torque is produced. We know that the moving coil is wound on a aluminium former, right? So this aluminium former is a non-magnetic material, so it acts as a conductor, right? This moving coil is wound on aluminium former. It's a non-magnetic material, so it acts as a conductor. So when this, we know that this moving coil is placed in a magnetic field of a permanent magnet. When the coil moves, the moving coil moves, the aluminium former on which the moving coil is wound also moves in the magnetic field of the permanent magnet. So this aluminium former acts as a conductor. We know that when a conductor cuts the flux and EMF is induced in that conductor. When the conductor cuts the flux, an EMF will be induced in that conductor. So here the conductor is the aluminium former on which the moving coil is wound. When the moving coil is moving, the aluminium former also moves, so it cuts the magnetic field produced by the permanent magnet. So what happens is an EMF is induced in this aluminium former which acts as a conductor. So this EMF induces a small circulating current in the aluminium former. It is called as eddy currents. So when the conductor, that is aluminium former, cuts the field flux produced by this permanent magnet, an EMF will be induced in that aluminium former since it is a closed circuit. So because of that EMF, eddy current will be induced in that aluminium former. So as per Lenz's law, we know that this eddy current will produce a force or torque which eddy current produces a force or torque which opposes the cause producing it. So what happens is this eddy current will produce a force or torque which opposes the cause producing it. The cause producing is nothing but the movement of the moving coil, right? So as per Lenz's law, this eddy current will produce a torque. That torque is called as damping torque. So this damping torque will damps the oscillations in the pointer, damp out the oscillations in the pointer so that this final steady state position is easily reached. So until now we have seen what is construction and working of D-Osnovel galvanometer. In the construction of D-Osnovel galvanometer, we are having a permanent magnet for producing uniform radial and horizontal magnetic field, and a moving coil which will be wound on aluminium former will be placed in between the air gap of the permanent magnet, and the moving coil will be suspended with the help of a suspension, right? That suspension have a upper and lower springs which is used for controlling torque, right? So principle of operation is, when a current carrying conductor is placed in a magnetic field, it experiences a force, right? So the current carrying conductor is the moving coil. When a current flows through this moving coil, what happens is it is placed in a magnetic field. So the current carrying coil will experiences a force so that the coil moves in that magnetic field, right? So this coil along with the iron core is placed in between the permanent magnet, is suspended with the help of a spindle in case of portable galvanometers. So when the coil moves, along with that coil the spindle also moves, and with the spindle the pointer will be attached, so that what happens when the coil moves, the pointer also moves. The pointer moves over the graduated scale, will indicate the current flowing through that galvanometer, right? This one is the operation of moving coil D'Arsnoval galvanometer. Next one is, when the coil moves, the deflection of the pointer will be directly proportional to the amount of current flowing through the coil, right. Now we have to damp out the oscillations of the pointer in order to reach its final steady state position quickly. So in order to damp out the steady state oscillations, we are producing a damping torque. That damping torque is produced because of that aluminium former on which the moving coil is found. The aluminium former along with that moving coil moves in a magnetic field. According to that, an EMF will be induced in the aluminium former. So because of that EMF, eddy current will be induced in that aluminium former. This eddy current will produce a opposing force to the movement of the coil as per Lenz's law. So this opposing torque or force is called as damping torque, which will damp the oscillations of the pointer and will make the pointer to rest at the final steady state position quickly. Another torque called controlling torque will be produced, which will oppose the deflection torque and will make the pointer to balance at a equilibrium position. So this is the working of D'Arsnoval galvanometer. Next we will see the torque equation of D'Arsnoval galvanometer. Next we will see the torque equation of D'Arsnoval galvanometer. So from the diagram we know that L is the length of coil side, N is the number of turns in the coil, B is the flux density in the air gap, which is expressed in Weber per meter square, I is the current flowing through moving coil, K is the spring constant, which is expressed in Newton per radians, theta is the deflection of the pointer in radian, and D is the width of the coil side. So L is the length of the coil, N is the number of turns in the coil, B is the flux density in the air gap, I is the current flowing through the moving coil, K is the spring constant, theta is the deflection of the pointer, and D is the width of the coil side. So first we will calculate the force on each side of the coil, which will be given by the flux density B, the current flowing through the moving coil, and length L in newtons. Here, since we know that the moving coil is placed in a radial field, the field is radial, the angle alpha will be equal to 90 degree. So we know that sin alpha equal to sin 90 degree equal to 1. So we will get BIL newtons, the force on the each side of the coil. So here alpha is the angle between direction of magnetic field and conductor. So here, since the coil has n turns and each turn has two sides, total force equal to 2 NBIL newtons. So we have calculated the total force. Next, the deflecting torque, deflecting torque, which is represented Td, is equal to force into distance. Already we have calculated the force, which is equal to 2NBIL into the distance. So 2NBIL into D is the deflection torque D. So we can rearrange this equation, 2NBIL into D. So length into depth is the area, BI, I am replacing it with area A. A is the area of the coil. Here A is the area of coil in meter square. Here N, B, A are all number of turns, flux density, and the area are all constants of the galvanometer. So the deflection torque Td can be written as Td is equal to G into I, where G is equal to NBA, which is called as displacement constant. Next, the controlling torque exerted by the suspension at deflection theta is given by, controlling torque is expressed by Tc, which is equal to K into theta, where K is the spring constant. K is the spring constant. So for steady deflection, the deflection torque Td must be equal to the controlling torque Tc. So for deflection torque we can write G into Y, Tc is equal to K into theta. So the current I will be equal to K into theta by G. So from this K and G are the constants, we can say that the current is directly proportional to deflection. So the current flowing through the moving coil will be directly proportional to the deflection of the pointer. So we can replace the values of G also, and also we can find the equation for theta from this equation. So by rearranging the equation, you will have theta is equal to Gi by K. So you can substitute the values of G as N, B, A, I divided by K. So the current will be directly proportional to the deflection of the pointer. So here several times the deflection is measured, and the scale is kept at a distance of 1 meter from the mirror. How the reading is, indication is given is, a light will be projected on the lamp and it will be reflected on the scale. So for indication we have used a mirror on which the light is projected with the help of a lamp, and since the mirror is placed on the taut suspension, when the moving coil moves, the mirror also moves, and that light will be reflected on the scale. From that the readings will be taken. So in today's class we have seen the construction and working of D'Arsnoval galvanometer, and we have derived the torque equation. Next class we will see the other type of instruments. Thank you.